What you're about to witness involves forces strong enough to reshape solid metal in seconds. Massive systems operating with relentless precision. This isn't just manufacturing, this is industrial power at its absolute peak.
The steel production process begins with the careful selection and preparation of raw materials. Different types of scrap, including busheling, shredded scrap, and structural plates, are stored in an enclosed yard to protect them from contamination. These materials are then loaded into large buckets with a capacity of approximately 30 tons. Once prepared, the selected scrap is transported and charged into an electric arc furnace, where the melting phase begins. Inside the furnace, powerful electrodes generate intense heat, transforming the solid scrap into molten steel. At this early stage, the first additives are introduced to start refining the chemical composition and improving the overall quality of the steel. As the melting process continues, operators monitor the bath closely to ensure that it meets the required temperature and chemical parameters. Meanwhile, a ladle is preheated to prepare it for receiving the molten steel. Preheating is essential to prevent thermal shock and minimize heat loss during transfer. Once the desired temperature is reached, the molten steel is tapped from the furnace into the ladle. During this transfer, a first phase of refining continues with the addition of alloying elements, allowing the steel to begin forming its essential characteristics based on whether it is carbon steel or alloy steel. The ladle is then moved to the ladle metallurgy station, where further refinement takes place under strict control. Operators follow precise instructions provided by metallurgists and supported by advanced computer systems. At this stage, additional alloying elements are added in exact quantities to achieve the desired chemical composition. 3 electrodes maintain the temperature of the molten steel, ensuring it remains stable for further treatment. Argon gas is gently bubbled through the liquid metal, promoting the flotation of non-metallic inclusions toward the surface. These impurities are captured by a layer of synthetic slag, which also protects the steel from reoxidation. Oxygen levels are carefully controlled to ensure high cleanliness and quality. After degassing, the refined molten steel is ready for casting. It is poured into molds using a bottom pouring technique, which helps improve the internal structure and yield of the ingots. During this stage, argon shielding is applied to prevent reoxidation. The steel solidifies inside the molds, forming ingots of various sizes, typically ranging from 3 to 42 tons. Once solidified, the ingots are stripped from the molds and prepared for the next stage. While still at a high temperature, the ingots are transferred to preheating furnaces in the forging department. This rapid transfer minimizes heat loss and improves energy efficiency. The ingots are reheated to approximately 2,300 degrees Fahrenheit to reach the optimal forging temperature. Once heated, they are quickly moved to hydraulic presses for shaping. Forging is carried out using powerful presses, including a 5,000-ton press equipped with a rail-mounted manipulator capable of handling large and heavy pieces. The ingots undergo intense deformation using wide dies, which ensures a high level of internal structure refinement. This process is crucial for achieving superior mechanical properties and uniform microstructure. A second press with a capacity of 2,000 tons is used for smaller ingots, allowing for precise and complex shaping. Advanced manipulators and rotary tables enhance accuracy and reduce delays, ensuring efficient operation. Following forging, the shaped pieces are transferred to the heat treatment department. Here they undergo various controlled thermal processes such as annealing, normalizing, quenching, tempering, and stress relieving. Each treatment cycle is carefully programmed and monitored using modern furnace control systems to ensure uniform temperature distribution and consistent results. Controlled cooling, often using water or polymer solutions, ensures that the desired mechanical properties are achieved throughout the material. After heat treatment, the steel components undergo rigorous quality control procedures. Metallurgical analysis is performed to check the microstructure and cleanliness using advanced microscopes and digital analyzers. Mechanical testing, including tensile and impact tests, verifies that the material meets performance requirements. Statistical process control is applied throughout the entire production process to maintain consistency and traceability. The final stage involves machining and finishing operations. A wide range of equipment, including CNC lathes, milling machines, and boring machines, is used to achieve precise dimensions and surface finishes. Large components can be machined to exact specifications, and powerful saws are used to cut materials to the required sizes. Each finished piece is subjected to thorough inspection, including ultrasonic testing, dimensional checks, and hardness measurements. Through strict control at every stage from raw material selection to final inspection, the process ensures the production of high-quality steel with consistent properties and performance. The forging process of massive metal components begins with the preparation of high-grade steel produced in a modern steel mill, equipped with advanced technology and a complete fleet of machinery. Carefully selected raw materials are melted, refined, and cast into large ingots, which serve as the starting point for heavy forging operations. Once solidified, the ingots are reheated in controlled furnaces to reach the required forging temperature. The heated material is then transferred to powerful hydraulic presses, including 3,200-ton and 6,000-ton units, where intense force is applied to shape the steel. Through repeated pressing and deformation, the structure of the metal is refined, improving its strength and mechanical properties. The facility is capable of producing forgings with a maximum weight of up to 50 tons, demonstrating its capacity for handling extremely large components. After forging, the parts undergo precise heat treatment processes to enhance durability, toughness, and performance. Computerized control systems continuously monitor temperature, pressure, and timing to ensure consistent quality and innovation in production. Following heat treatment, the components are subjected to high-precision machining operations, where surfaces are finished to exact specifications. Finally, ultrasonic inspection devices are used to detect internal flaws, ensuring excellence and reliability in every forged product.
China's steel forging industry has achieved technological feats that redefine industrial capabilities on a global scale. Within state-of-the-art factories, massive forging presses exert forces of thousands of tons, transforming raw steel billets into complex shapes with unparalleled precision. These facilities integrate automated material handling, computer-controlled hydraulic systems, and high-speed sensors, ensuring that every forged component meets exacting standards for structural integrity and dimensional accuracy. After preheating steel billets and furnaces, equipped with advanced temperature monitoring and uniform heating systems, consistency in temperature is critical, as it directly influences the metal's malleability and the final mechanical properties. Billets are transferred to forging presses where sophisticated hydraulic and mechanical systems shape the steel under immense pressure. Engineers carefully control force, speed, and deformation patterns to optimize grain flow, enhancing strength, toughness, and fatigue resistance. Automation plays a pivotal role in China's steel forging technology. Robotic arms, control software, manage the precise positioning of billets, coordinate forging sequences, and adjust parameters in real time based on sensor feedback. This minimizes human error, improves efficiency, and allows for the production of highly complex components that were previously impossible to achieve consistently. Post-forging, components undergo heat treatment, quenching, and tempering processes tailored to the specific alloy and application. Cutting-edge furnaces, controlled by digital systems, ensure uniform cooling and tempering, stabilizing the microstructure and maximizing performance characteristics. China's investment in high-speed forging lines, precision dies, and integrated production monitoring systems has pushed the limits of scale and complexity. Components ranging from massive turbine shafts and ship propellers to intricate automotive parts are produced with remarkable repeatability and reliability. The seamless integration of metallurgy, mechanical engineering, and digital control positions China's steel forging capabilities at the forefront of global manufacturing. The combination of enormous industrial scale, precision engineering, and technological innovation demonstrates that China's manufacturing level is far beyond conventional expectations. By continuously upgrading equipment, refining processes, and integrating in automation, Chinese steel forging facilities exemplify the future of heavy industry, where efficiency, quality, and technological sophistication converge to produce materials capable of withstanding extreme mechanical and environmental demands. It began with a simple idea, the wheel, a force that quietly shaped civilizations and powered human progress. Deep in rural Bihar, the rail wheel plant Bella carries that legacy forward, where molten steel is transformed into the backbone of modern railways. Inside this facility, advanced bottom pressure pouring technology channels liquid metal into graphite molds with precision, ensuring uniform structure and strength. At peak capacity, a new wheel emerges every few minutes, each engineered for durability, balance, and long-term performance under extreme loads. Despite its remote setting, the plant operates with world-class standards, integrating metallurgical control, heat treatment, and rigorous laboratory testing. What once struggled below capacity has surged beyond expectations, driven by disciplined process optimization and relentless teamwork. Here, in the quiet countryside, innovation meets determination, proving that even the most unassuming place can forge components that keep an entire nation moving. The Lucchini Steelworks employs advanced industrial techniques to produce high-quality rail materials. Water drawn from Lake Iseo is filtered and used for cooling in all stages of steel processing, ensuring precise temperature control during quenching and heat treatment. Furnaces operate continuously, maintaining high temperatures essential for melting, alloying, and refining steel. The facility manufactures wheels, rims, and rails, employing automated handling systems and controlled cooling tanks to ensure uniform mechanical properties, dimensional accuracy, and durability. The quenching process generates controlled steam, optimizing microstructure and hardness. Modern monitoring systems track temperature, water flow, and furnace conditions to maintain consistent quality across production batches. These integrated techniques allow the plant to produce components suitable for global rail applications, combining metallurgy, thermodynamics, and process engineering to deliver high-performance railway materials efficiently and reliably. In the heart of Lucchini RS, a new era of railway wheel manufacturing unfolds with cinematic grandeur. The rolling mill stretches across the factory floor, a seamless symphony of steel and precision, where no intermediate warehousing interrupts the flow of production. A rotating furnace, 23 meters in diameter, roars to life, consuming 40 tons of raw steel every hour, transforming cold metal into glowing, malleable perfection. Two Titanic hydraulic presses, one capable of 9,000 tons and the other 5,000 tons, descend with monumental force, sculpting the steel into wheels that will carry entire trains across continents. Every 58 seconds, the rhythm of creation produces a new wheel, a testament to human ingenuity and the relentless march of industrial power. A rolling machine with 13 computer-controlled axes dances with precision, guiding the steel into dimensions up to 450 millimeters with mechanical grace. Each wheel emerges not just as a component, but as a crafted marvel, destined for the rigors of the rail. Beyond shaping, the heat treatment line imbues each wheel with strength, resilience, and durability, ensuring it withstands the harshest journeys. Lucchini RS's rolling mill is not just a factory, it is a stage where raw metal becomes legend, where every wheel tells a story of innovation, power, and mastery. Lucchini RS produces high-performance railway components engineered for modern trains. Its products include wheels, axles, tires, and complete wheel sets, designed for durability, precision, and reliability. Manufacturing processes involve steel casting, forging, rolling, heat treatment, and machining to achieve optimal mechanical properties and geometric accuracy. Wheels are optimized for wear resistance, low noise, and structural integrity. Axles and wheel sets are designed for strength and fatigue resistance. Tires use advanced metallurgical techniques to extend service life. Customized solutions are available to meet specific operational requirements, ensuring safety, efficiency, and long-term performance in rail transportation systems. It starts with raw steel, heated, glowing, alive, ready to be transformed into one of the most critical components in rail engineering, the axle. At Lucchini RS's Axle Forge, immense hydraulic presses shape each billet under controlled force, aligning the internal grain structure for maximum strength and fatigue resistance. Precision machining follows, refining geometry to exact tolerances measured in microns. Heat treatment enhances durability, ensuring performance under extreme loads and constant stress. Every axle undergoes rigorous testing, where metallurgy meets engineering discipline, delivering reliability that keeps trains moving safely across vast distances. In modern rail manufacturing, precision is no longer crafted, it is orchestrated. Inside Danobat's automated axle production line, raw forged shafts enter a fully integrated system where every movement is calculated, every micron controlled. Robotic handling systems guide each axle through a sequence of high-performance machines, rough turning, finish machining, and precision grinding without human intervention. A centralized control system synchronizes the entire line, enabling autonomous operation, real-time monitoring, and adaptive process optimization. Advanced CNC lathes and grinding units refine geometry to exact tolerances, while non-destructive testing, ultrasonic, and magnetic inspection ensures structural integrity at every stage. This is not just manufacturing. It is a fully digital, turnkey ecosystem where automation, data, and engineering converge, producing railway axles with unmatched consistency, efficiency, and reliability for the demands of high-speed rail. In the heart of the UK's rail engineering network, precision meets power at LH Group's Advanced Overhaul facility in Staffordshire. Years of continuous investment have shaped a high-tech hub where wheel sets, bogies, and final drives are restored to peak performance with uncompromising accuracy. Here, skilled engineers manage the complete life cycle of critical rail components, delivering services from rewheeling and reprofiling to non-destructive testing and bearing inspection. A 400-ton wheel press anchors the operation, supported by wheel shrink fitting systems, computerized reprofiling lathes, and dynamic balancing technology that ensures smooth, stable operation at speed. Advanced inspection methods, including ultrasonic testing and magnetic particle inspection, validate structural integrity at every stage. The facility handles everything from locomotive and freight wheel sets to passenger and infrastructure applications, all within a fully integrated, one-stop environment. Every process is aligned with strict railway safety standards, where engineering discipline, advanced tooling, and experience converge to keep rail systems moving with confidence. It begins not with creation, but with restoration. Inside the maintenance bay, worn railway wheel sets arrive, carrying the silent imprint of thousands of kilometers. At the center of this precision-driven process stands the Danobat DPL 2600, a CNC-controlled portal lathe engineered to redefine wheel set reprofiling. Built with a roll-through configuration, the system allows complete wheel sets to pass directly through the machine, minimizing handling time and maximizing operational efficiency. Once positioned, synchronized cutting tools engage both wheels simultaneously, restoring tread profiles with exceptional accuracy and repeatability. The DPL 2600 is designed to handle wheel sets up to two 600 millimeters in diameter, with high torque drives and rigid structural construction ensuring stability during heavy-duty machining. Advanced CNC control manages cutting parameters in real time, adjusting feed rates, tool paths, and depth of cut to maintain optimal surface finish and dimensional precision. Integrated measurement systems verify geometry throughout the process, ensuring compliance with strict railway standards. This combination of automation, power, and precision transforms worn components into fully restored wheel sets, extending service life, enhancing safety, and keeping rail operations running with uncompromising reliability.
The manufacturing of helical submerged arc welded line pipes at Man Industries India Limited is carried out through a highly advanced and precisely controlled process, ensuring high-quality products for global applications. These pipes are widely used in sectors such as oil and gas transportation, water supply, sewage systems, agriculture, and construction, reflecting their versatility and reliability. The process begins with thorough coil inspection to ensure the raw material meets required standards. The coil is then placed and leveled before being joined to form a continuous strip. Advanced ultrasonic testing is applied at this stage to detect any internal defects. Next, the edges of the coil are milled to prepare them for accurate welding. The strip is then formed into a spiral pipe shape, followed by precise plasma cutting. Subsequently, submerged arc welding is performed both inside and outside the pipe to ensure strong and durable joints. After welding, excess material is removed and visual inspection is conducted. The pipes then undergo real-time radiographic testing, end chamfering, and hydrostatic testing to verify strength and leak resistance. Further quality checks include ultrasonic testing, X-ray testing, and magnetic particle inspection, ensuring defect-free products. A final inspection, including third-party verification, is completed before marking. Man Industries emphasizes continuous innovation and rigorous testing, supported by an in-house laboratory meeting international standards, combining craftsmanship, sustainability, and excellence in every product. The video of Wasserkraft Volk AG presents a comprehensive overview of a company where turbines and generators are manufactured under one roof. With a long tradition of craftsmanship, the company combines creativity with state-of-the-art manufacturing technology to produce high-end products efficiently and economically. This approach supports the development of a sustainable energy sector, where hydropower plays a crucial role as a reliable, renewable energy source. At the core of the company's success is its strong engineering expertise. Each hydropower plant is carefully planned by experienced engineers specializing in hydraulic, mechanical, electrical, and control engineering. This multidisciplinary knowledge ensures optimal system design and long-term operational reliability for customers. The company also operates its own turbine test rig, allowing for precise testing and performance evaluation. A key advantage is the ability to provide multiple turbine types from a single source, including Francis, Pelton, Turgo, and cross-flow turbines. This flexibility allows the company to adapt to various water conditions and project requirements. Its product range starts from small systems of around 300 kilowatts and extends up to powerful turbines reaching 25 megawatts. Modern machining equipment guarantees maximum precision in production. All components are carefully sealed and coated, ensuring durability and long service life. Additionally, turbine systems are pre-assembled at the factory, enabling faster and more efficient installation on site. Uniquely, the company also manufactures synchronous generators in-house, from coil production to final testing. Advanced rotor winding and impregnation technologies ensure high mechanical and electrical strength. Each machine undergoes thorough testing, with detailed reports provided to customers, ensuring transparency, quality, and reliability. The largest steel production facility of the German Water and Energy Group is located in a picturesque area between the Harz and Kyffhäuser Mountains in Nordhausen. This plant specializes in manufacturing high-quality stainless steel products, including casing and screen pipes for well construction, as well as components for well completion. One of its most distinctive products is the wire wrap screen, produced in diameters ranging from 32 to 1,000 millimeters and in various stainless steel grades. The production process begins with the preparation of raw materials such as steel sheets, flat bars, and fittings. In the pipe workshop, metal sheets are shaped into cylindrical forms using a 4-roll bending machine, followed by tack welding. The longitudinal seam is then welded externally using submerged arc welding and internally on another machine to ensure strength and durability. Pipe sections can be joined together, and connectors are welded onto the ends according to customer requirements. For wire wrap screens, supporting wires are first arranged, and a triangular profile wire is wound around them. Each intersection is welded using resistance welding with high current and controlled cooling. This ensures precise slot dimensions and structural stability. After fabrication, all products undergo pickling and passivation to enhance corrosion resistance. Finally, after strict quality inspection, the finished products are carefully packed and prepared for delivery.
The manufacturing of Linke-Hofmann-Busch coaches at the modern coach factory in Re Barelli represents a benchmark in contemporary rail engineering, defined by automation, precision, and integrated production systems. MCF has evolved into one of the most advanced rail coach manufacturing units in the world, adopting state-of-the-art technologies and Industry 4.0 principles. The production ecosystem at MCF is structured across 5 primary shops: the shell shop, paint shop, Bogie shop, wheel shop, and furnishing shop, supported by auxiliary units, utilities, and automated storage systems. Each shop operates as a highly specialized node within a synchronized manufacturing chain, ensuring efficiency, traceability, and consistent quality output. Fabrication begins in the shell shop, a facility extending nearly 900 meters, where raw steel coils are processed into structural components. Steel sheets are uncoiled and cut to required lengths before undergoing high-precision CNC laser cutting. These sheets are then transformed into various structural skins and components using advanced laser welding and forming technologies. The integration of CNC press brakes, hydraulic presses, and stretch forming machines enables the production of high-strength, dimensionally accurate components entirely in-house. Within the shell shop, 4 critical subassemblies are fabricated: sidewalls, underframe, roof, and end walls. Sidewall panels, initially laser welded, are reinforced with stiffeners using robotic welding systems to enhance structural integrity against dynamic loads. Robotic spot welding ensures uniform joining of seams, while specialized manipulators assemble curved sections such as car lines. The underframe, serving as the backbone of the coach, is constructed on automated robotic welding lines. Pre-assembled structures are tack welded and then subjected to precision robotic welding across multiple stations. Additional support brackets and mounting structures are integrated to accommodate onboard equipment. Roof assemblies are produced using corrugated sheets reinforced with Z-shaped arches, joined through robotic spot welding systems equipped with laser guidance for accuracy. Similarly, end walls are fabricated using jig-based tack welding followed by robotic welding operations to ensure geometric consistency and strength. These 4 subassemblies are brought together in a cathedral jig, a mechanized fixture designed to maintain dimensional accuracy during final shell assembly. Robotic welding systems equipped with laser sensors identify joint locations and execute high-quality welds, forming a unified and robust shell structure. Post-assembly processes include skin tensioning to eliminate surface deformation and the integration of internal mounting supports. Following shell fabrication, the structure is transferred to the paint shop. Surface preparation begins with abrasive blasting to remove contaminants and improve coating adhesion. The shells are then painted in automated booths using polyurethane coatings, ensuring durability, corrosion resistance, and a high-quality finish. Controlled ovens facilitate proper curing of the paint layers. The painted shell proceeds to the furnishing shop, where interior systems are installed across multiple assembly lines. This stage includes thermal insulation, flooring installation, and the integration of doors, windows, partitions, and electrical wiring. Interior paneling of walls and ceilings is completed alongside the installation of lighting systems, air conditioning units, and passenger amenities. Seating arrangements, including berths, are mounted as the coach nears completion. Parallel to shell production, the Bogie shop manufactures the undercarriage assemblies. Steel plates are straightened, cut using underwater plasma technology, and cleaned via blasting processes. Components are formed using press bending machines and assembled into Bogie frames through robotic welding lines. These frames undergo rigorous inspection, machining on 5-axis CNC systems, and dimensional verification using coordinate measuring machines, CMM. Final assembly integrates suspension, braking, and structural components, followed by static load testing to simulate operational conditions. In the wheel shop, axle and wheelset production is executed through a highly automated sequence involving multiple CNC machines. Axles are machined, drilled, turned, and ground to precise specifications before undergoing quality testing. Wheel discs are machined separately and matched to axles using data-integrated systems to ensure perfect interference fits. CNC wheel presses assemble the components, followed by profiling, balancing, and bearing installation. Each wheel set is subjected to stringent quality checks to guarantee operational safety. The final stage involves mating the furnished coach body with the completed bogies and wheel sets. The assembled coaches undergo comprehensive testing, including load simulations, water leakage, shower tests, and validation of electrical and air conditioning systems. Only after passing all quality and safety benchmarks are the coaches cleared for deployment. Supporting the production line is a robust back-end infrastructure, including automated storage and retrieval systems that streamline material handling and inventory management. Continuous training programs ensure that personnel remain proficient in advanced manufacturing technologies. Additionally, MCF emphasizes innovation through dedicated design centers and collaboration with international inspection agencies to meet global standards. The factory has demonstrated significant production scalability, with ambitions to reach outputs exceeding 1,500 coaches annually. Adoption of Industry 4.0 technologies, including digital monitoring and smart manufacturing systems, positions MCF at the forefront of global rail coach production. Beyond manufacturing, the MCF ecosystem includes a modern township equipped with advanced infrastructure, security systems, and sustainable initiatives such as solar power generation. These developments contribute to a comprehensive environment supporting both industrial excellence and workforce well-being. Through its integration of advanced engineering, automation, and quality assurance, the modern coach factory in Ray Borelli exemplifies the future of rail coach manufacturing, delivering high-performance LHB coaches that meet international standards of safety, comfort, and reliability. Reliability on the rails is not accidental. It is built through meticulous overhaul processes where every wheel set and bogie is restored to peak condition. The facility undertakes complete refurbishment and conversion of locomotive, passenger rolling stock, and freight wagon bogies. This includes comprehensive overhaul of wheel sets, brake equipment, suspension systems, dampers, and axle assemblies. With recess accreditation and a capacity of up to 1,500 bogie overhauls annually, operations are optimized for both scale and responsiveness, including rapid turnaround options as short as 48 hours. Wheelset overhaul is executed using state-of-the-art CNC systems, such as the Hagenscheidt PM 1-190 Machining Center, which performs pre-machining inspection and precise gauging before reprofiling or rehealing. Additional processes include axle renewal, bearing replacement, and gearbox refurbishment. Integrity is verified through ultrasonic, magnetic particle, and eddy current testing to eliminate defects and ensure operational safety. Complementing this, the wheel shop is equipped with CNC axle lathes, vertical borers, wheel presses, and balancing machines. Finished assemblies are coated using advanced painting systems. Through lifecycle engineering and fleet management services, Wabtec enhances durability, reduces maintenance costs, and maximizes asset availability for rail operators. Extending the life of rail vehicles is no longer just about repair, but about intelligent refurbishment driven by engineering precision and innovation. The overhaul process extends beyond mechanical systems to include bogies, wheel sets, and braking assemblies, supported by advanced lifting infrastructure capable of handling all types of rolling stock. A key priority is minimizing downtime while extending service life through targeted upgrades and adaptive redesigns. Interior refurbishment programs encompass flooring replacement, installation of passenger information systems, CCTV, OTMR recorders, and modern seating layouts, including PRM-compliant configurations that enhance accessibility. Complementing these upgrades, ultra-modern repainting facilities apply advanced coating systems to vehicles up to 23 meters in length, ensuring both durability and visual quality. Wabtec also delivers specialized accident repair services, restoring damaged vehicles using certified procedures and full electrical testing capabilities. Supported by expert divisions across systems such as HVAC, doors, and traction, the company provides flexible on-site and off-site solutions, delivering reliable, efficient, and future-ready rail assets. The C4 project at Slade Green Maintenance Depot represents a critical phase in the lifecycle management of modern rolling stock, focusing on the comprehensive overhaul of bogies, the fundamental load-bearing and guidance systems beneath each rail coach. This intervention is not merely routine maintenance. It is a deeply engineered process designed to restore structural integrity, optimize dynamic performance, and ensure compliance with stringent safety standards. At the core of the bogie overhaul process lies systematic disassembly. Each bogie is separated from the coach body and stripped down into its primary components, including wheel sets, axle boxes, suspension elements, brake systems, and the bogie frame itself. This level of teardown enables precise inspection and condition assessment, supported by non-destructive testing methods such as ultrasonic and magnetic particle inspection to detect fatigue cracks or microstructural defects. Wheel sets undergo detailed profiling and dimensional verification, with CNC-controlled lathes restoring wheel tread geometry to exact tolerances. Axles are inspected for concentricity and surface integrity, ensuring reliable load transmission at high speeds. Simultaneously, suspension systems, including primary and secondary springs, dampers, and linkages, are either refurbished or replaced to maintain ride stability and passenger comfort. The bogie frame, often subjected to significant cyclic stresses, is carefully examined for distortion or weld degradation. Where necessary, corrective machining and robotic welding techniques are applied to restore structural accuracy. Brake assemblies are reconditioned with renewed friction elements, actuators, and control interfaces, ensuring responsive and consistent braking performance under operational loads. Reassembly follows a tightly controlled sequence, integrating refurbished and new components into a fully functional bogie unit. Precision alignment and torque calibration are essential at this stage, as even minor deviations can impact tracking behavior and wear characteristics. Once assembled, the bogie is subjected to static and dynamic testing regimes that simulate real-world service conditions, verifying load distribution, suspension response, and braking efficiency. The C4 overhaul program ultimately extends the operational lifespan of rolling stock while reducing failure risks and maintenance costs. At Slade Green, the integration of advanced diagnostics, mechanized handling systems, and skilled engineering oversight ensures that each bogie returns to service with performance characteristics closely matching those of a newly manufactured unit. UAB Vitras operates as a highly specialized contractor in railway infrastructure engineering, delivering synchronized solutions across track construction, repair, and overhead electrification systems. Within modern rail networks, the integration of mechanical track systems and electrical power supply infrastructure defines operational efficiency, safety margins, and long-term durability. Railway construction activities are executed through a sequence of controlled engineering stages, beginning with subgrade stabilization and load-bearing preparation. Soil layers are compacted and reinforced to ensure long-term resistance to cyclic loading. Ballast is then distributed and tamped to achieve uniform load transfer, followed by the installation of sleepers and rails aligned to strict geometric tolerances. Advanced tamping, lining, and leveling machines are deployed to maintain precision, ensuring smooth vehicle dynamics and reduced track degradation over time. Parallel to track systems, overhead contact line infrastructure is installed to provide continuous electrical power for train operation. This process includes the erection of steel or concrete masts, installation of cantilever brackets, and integration of tensioning systems. Contact and messenger wires are strung under controlled tension with parameters such as height, stagger, and tension carefully calibrated to maintain stable interaction with the pantograph at varying speeds and environmental conditions. Precision measurement and adjustment are essential to prevent arcing, excessive wear, and energy losses. Maintenance operations are equally critical and focus on sustaining both structural and electrical performance. Track systems undergo routine inspection, rail grinding, welding, and geometry correction to address wear, deformation, and alignment deviations. Overhead systems are inspected for contact wire wear, component fatigue, and tension imbalance. Preventative maintenance includes retensioning, replacement of insulators and droppers, and recalibration of support assemblies. Through the integration of advanced machinery, diagnostic technologies, and disciplined engineering processes, UAB Vitras ensures railway infrastructure operates within strict technical parameters, supporting safe, efficient, and high-performance rail transport systems.